guys, in this tutorial we will talk about linear regression. So let's get to it. So linear regression is one of those fundamental machine learning models that anyone in the machine learning needs to know really well. Okay, so first let's start by highlighting a couple of important components associated to linear regression. So linear regression falls under what is called supervised learning. And basically that means that there will be a target variable that we want to model. So there is a target variable to be modeled. Okay. Model as a function of a set of another input variables. Okay. So that's basically what linear regression is. Now, there is an important component when it comes to linear regression. As the name suggests, so we're going to make an assumption that the relationship between the input variables and the target variable is linear. So assumes linearity. Okay, which it may be applicable in some cases, but for most of the cases or for most of the data sets out there, the assumption of linearity is not going to be satisfied. Okay, so those are the two things that I want to highlight about linear regression before we go into more details about what linear regression is, how the model looks like, and how the parameters that they are listed in the model are estimated. Okay, so it's supervised learning because there is a target variable that it needs to be modeled as a function of the input variables. Linearity assumption. All right, so section 1, introduction to linear regression. So linear regression is a fundamental algorithm in supervised machine learning that is used to model the relationship between a set of dependent variables and one or more independent variables. Okay, it assumes a linear relationship between the inputs and the outputs. Section 2, mathematical foundation. So basically, when you are building a linear regression model, so you make the following assumption. The y is a linear relationship of the inputs. So then here we have x1 is one of the inputs, x2 is another of the inputs. In general, xn is another of the inputs. So then in this case, we are modeling y as a linear function of x1, x2, all the way up to xn. Now, the other thing that I want to highlight here is that notice beta 0, beta 1, beta 2, beta n. Those are the parameters. Okay, beta 0 is referred as the intercept of the line. Beta 1 is referred as the slope associated to x1. Beta 2 is the slope associated to x2, and so on. So all of those betas, so those are parameters, okay? And the model depends on those parameters, because if we want to use this model to make a prediction on y, so we need actual values, okay? So now let's get into what is the idea behind how those parameters are estimated. So the best way, at least how I learned this particular technique, is by just a quick visualization. So let's keep things simple. So we're going to assume that we have a y and then you have an x. Okay, and let's assume that this is our data. Okay, so when I look at that, it seems like the relationship between x and y seems linear. So it is reasonable to make the following assumption, that I can see a line going this way. Okay, but someone else can say, okay, I can see maybe other line, right? Maybe I prefer this line, right? Maybe someone else says, no, I like this line. And as you can see, there are many different options. So there has to be some sort of like a mechanism that will help us to define what is, in some sense, the baseline for the data at hand. And that's where this idea behind of ordinary least square comes to the picture. So ordinary least squares. Okay, so then the idea here is the following. So again, let's go back to the picture that we have before. So we have y and then we have x. Here we have the data, right? Now, ordinary least square, basically what it does is the following. So it will select the line, but it will select the line in such a way that the residual sum of squares is minimized. Okay, now let's talk about first the residuals first. So then the residuals basically is defined as the difference between what the model is predicting and the actual value. So then here, when you look at that gap between the actual data point and what the line is predicting, that is called the residual. So we can call this R1. Similarly, we can say this is R2, R3, R4, R5, 6, 7, 8, 9, 10, and 11. Okay, so we have 11 data points, so we have 11 residuals. So the ordinary least square basically is an optimization routine that does the following. So then the goal is to minimize the residual sum of squares. So then basically it's just minimize this expression. R1 square plus R2 square plus R3 square plus dot dot dot. In this case, R10 square plus R11 square. So we're minimizing that expression. Okay, so we are finding, or at least this technique called ordinary least squares, it will find the line so that the residual sum of squares is minimized. That's basically the idea how these parameters that we see here, right? Beta 0, beta 1, beta 2, all the way to beta n, that's how those parameters are going to be estimated. So they're going to be estimated in such a way that the residual sum of the squares is minimized. Okay, or some statisticians, they refer to this as the mean square error, right? So then this is more formal. So then here you have the true value. Let me write this more clear. So this is the true value, right? And anytime that you see hats, especially in statistics and machine learning in general, so that refers is an estimate. So this is the model prediction. So what we're doing is, again, what the ordinary least square is doing is comparing the true value with what the model is predicting by taking the difference between those two, squaring that, and then adding up for all the values in the data, and then divide that by how many values do we have. Okay, so then the goal is to find the set of parameters so that the MSE is minimized. That's basically it. Okay, so that's basically how this technique called ordinary least square estimate values for the parameters using the data at hand. Now, once you have specific values for those parameters, then at that point you can plug values for x1, x2, all the way to xn, and compute the corresponding y value. So then at that point, you are just using the model to make predictions. Okay. All right. Let's move to the next section. So applications in data science. So linear model is one of those models that is being around for many decades by now, and is being applied on many different fields. So it's being applied in finance. So then typically if you want to, build a very simple model that predicts stock prices or stock returns, you can use a linear regression model. You can use it in marketing application, right? If you want to estimate how effective a specific marketing campaign is in terms of in terms of sales, yeah, so you can use a linear regression model. In real estate, you can use property features as the inputs to predict the property price. In operations in general, so if you want to forecast, I don't know, energy demand, so that could be another application of linear regression. Let's move to the next section. What are the pros of linear regression or of the linear regression model? It's simple and interpretable. It's really easy and fast to train. It's a good starting point. Okay. Yeah. So those are some of the pros associated to linear regression. It's simple, easy to understand. You can train or you can build a model really easily, and it's a good baseline. Okay. Yeah. I seen linear regression being applied on many different scenarios. Yeah. So one of the big plus is that if you're working for corporate America in general, right, and then there happens to be a strong linear relationship among the features that you are analyzing, so then linear regression should be the first model that comes to mind as a way to analyze that data. Not only that assuming that the model seems to be appropriate when you are delivering those insights, so stakeholders are going to be able to easily understand what's happening. So linear model is just one of those models that there is very, very easy to explain to others. Okay. Cons of linear regression. By far the biggest one is that it assumes linearity, which again, it may be appropriate for some cases, but in general, it's not going to be the case. Why is that? Well, it has to do with the world that we live in, right? The world that we live in is very messy and complex, and then most of the relationships out there that comes or that were generated from real life processes, they're going to be very non-linear in nature. So linearity probably is going to be an incorrect assumption there. Another con of linear regression is very sensitive to outliers. And outliers, they're going to be there pretty much in any in any real life data set. So outlier is one of those things that practitioners, they need to get comfortable with. Have some ideas in mind of how to work with them. Okay, so if you have outliers in your data and you're building a linear regression model, probably the model is going to get affected by that outlier. Multicollinearity issues. So then basically that has to do with, when you're building a model, right, a linear regression model in particular, and you have a bunch of input variables, right? So there is a chance that some of those input variables are going to be highly correlated with each other. And when that happens, the effect that you see is that the results that you get out of the parameter estimation is going to be unstable. Okay, so then those estimated values for the betas are not going to be reliable. Why? Because there is a whole linear algebra proof that shows that when you have columns that they are highly correlated among each others, the estimates that you get out of that estimation procedure is not reliable. Okay, and sometimes you may run into scenarios in which that the algorithm even is not going to be able to come up with estimates, okay, because there is high correlation among those variables. So multicollinearity, that's something that you need to keep an eye on, especially if you're building linear regression models. Okay. without proper regularization, the model can behave poorly. So linear regression models, basically, they are very sensitive not only to outliers, not only to multicollinearity, but also having inputs on different scales that will also have a negative effect in terms of model performance. So that's something that you need to keep an eye on, and regularization is also another big component there. Okay. When to use linear regression? So when the relationship between the inputs and outputs is approximately linear. Um, Believe it or not, um, there are some fields in which that's going to be true. So the first thing that comes to mind is in economics. There is a lot of, not a lot of, or at least I see some relationships that they are very linear in nature. Okay, so another use case that comes to mind is I a long time ago I did some analysis associated to geothermal data. That was uh, a very complex engineering process. So then in that case, when I was looking at the different KPIs that they were keeping track of with as inputs, and the target happens to be power, so then there was a strong linear relationship among them. So then there are some use cases that the linearity, it is the right way to model the data. So if you find yourself with a data set in which there is a strong linear relationship, just go ahead and build a linear regression model. When to use, another reason is when interpretability of the coefficient is important. And this is something that, again, you need to keep in mind when you're building models in general, right? So you need to keep a balance between interpretability and prediction power. So if the goal is to build a model because you want to be able to understand the relationships between the input variables and the target variable, so then you need to go with simpler models, and then linear regression falls into that category. On the other hand, if you only care about prediction power, so probably linear regression is not going to be the ideal model for that data set. So then in that case, you may rely on more complex algorithms that will probably outperform linear regression. Okay. Yeah, so then, and also you can use linear regression as a baseline for regression tasks. Okay. All right, so section 7 in summary. So linear regression is one of the most widely used and well understood models. Let me do this correctly. In data science, taught simple, it provides a solid foundation for understanding more complex regression and predictive modeling techniques. So yeah, by far, again, linear regression is one of those fundamental models that, once you have a good understanding of it, it will help you to start learning other models that may be more sophisticated in nature. Okay. All right. So then that's what I have for in terms of the notes. Now let's jump into one specific exercise that highlights how you can build linear regression models, take a look at the estimates, and use that model to make predictions. All right, guys. Now let's practice some of these linear regression model and how to build these type of models on a particular data set. So I'm going to use the same data file that I use in one of my previous tutorials. So then it's called calories. Again, just to give you a little bit of background, so then this is a data file or a data that was collected in a very simple study in which they were keeping track of some basic demographic on subjects, and then they kept track of how long they were working out, and then at the end they were estimating the number of calories that they were able to burn at the end of that workout session. Okay, so yeah, so we're gonna use that data file to build a linear regression model. So first we're going to start by importing the data. So for that, we're going to use pandas. So import pandas as PD. So reading the CSV file. So I'm going to call it df equals to PD read CSV. And then I think it's calories. Yes. So df, let's print the head. All right. So yeah. So then they collect the gender information, age, height, weight, duration of the workout, heart rate, body temperature, and the calories that they burn by the end of the workout session. So user ID doesn't provide us any information, so we can get rid of that. All right. So again, the goal is to use these columns right here, gender, age, height, weight, duration, heart rate, and body temperature to predict calories. And the model that we're going to use is a linear regression model. So first we're gonna start with something very simple. So we're gonna build a linear model, and we're only gonna use weight and age as the input variables to predict calories, okay? It's no calories intakes, it's calories burns. Calorie or calories, okay. All right, so for that, in this tutorial, I'm going to use one of the libraries that is called statsmodels formula. So then you can get to see more details about the parameters. Yeah, more information associated to those parameters. Okay, and the statsmodels formula is one of those libraries that provide that type of information. So let's start by loading that from statsmodels.formula API. And the function that we're gonna use is called OLS, and OLS stands for ordinary least square. All right, so here is the syntax. So here we're going to build the model, building the model, the linear model. So I like to use LMMD for linear model, then it's OLS. And then the syntax, if you are familiar with R programming, so it's gonna look very similar to R. So first you need to enter the target variable, which in this case is calories with uppercase C. So we start with, in quotes, we enter calories, then tilde thing, and then we list then after that we list the input variables or the name of the variables that we want to use as input, and we're going to separate them with a plus sign. So in this case we're going to use weight and age. So weight and age, and the data that we're going to use is the data frame that we just create. It's called df, and then fit. So up to this point, it will build the model again. It's called calories. Yeah, and then it will use weight and age as inputs. Calories will be the target. It will use the data frame called df. And then if we want to extract the results of the model, so we just do lm.summary. Okay, so here we have a bunch of stat results. So in this case, again, it tells us what is the dependent variable. It's called calories. The model is OLS. Here we have the R square. Here we have the adjusted R square. All of these are statistics metrics, right? That in some sense tell us how good the model is. So here we have the F stats. Here we have the AIC, the BIC, how many observations were used to build the model, the degree of freedom of the residuals. So all of this is just stats, okay? And I don't want to spend too much into it. So what I want to spend more time is here on this table. So this is the table that shows the estimates, right? The parameter estimate. So then here we have The estimated intercept is 58.77. The parameter associated to weight is 0.09. The parameter associated to age is 0.56. It is that this column right here shows the estimated standard error in those for those parameters. Here we have some p-values, okay? And typically the p-values, that is a statistical analysis. So the higher the p-value is, so then that means that that variable is less significant, and and you could remove it from the model in some sense. Basically, it just tells you that there is no linear relationship between that variable and the target variable. But in this case, using the standard 5% cutoff value or the 5% threshold as a reference, right? We see that all the p-values are less than that. So then that means that, weight and age in some sense are important variables and we should keep it in the model, okay? And then here you have some confidence intervals associated to each of those parameters. And typically the rule of thumb here is that, if you want to ignore the p-value column, you can, also use the confidence interval just to determine if, if the parameter happens to be, in some sense important, right? And the rule of thumb is just to look at the 95% confidence interval and check if 0 falls in that interval. If that is the case, meaning that if 0 falls in that interval, so then that means that that variable is not important and could be removed from the model. But in this case, none of the confidence interval contains 0, so then that means that all the variables at least are significant at a 5% significant level. Okay, so then that's basically how you can build a linear regression model with OLS, which is part of the stats model formula library. Now let's go to the next part. So here we're gonna build a model. Now we're gonna use calories as the target variable, and the other are going to be used as the input. So then basically now, instead of only using weight and age, so then now we're gonna use all of these. Okay. All right. So let me go back here. So we start with building the model, building the linear model. So ALM underscore MD equals to OLS. Now here we're gonna have calories. And now one thing that I want to highlight here is the following. Notice the gender, we have, label information stored there. And anytime that you have that type of variable with OLS, you need to add a C to it. So basically what we're doing here is we are telling Python, or in this case, we're telling stats models formula that gender is a categorical variable. That's basically what we're doing there. Okay, oops. Gender. And then we start with what was the other ones? So age, height, weight. So age, height, weight, duration, heart rate, body temperature. I think that's everything. Duration, heart rate, yes. Okay. So we build that and then display the model summary. Let's run this. Now we go to the parameter estimate table, which is here. Now we have an estimate parameter for each variable. And one thing that I want to highlight here is that notice that for gender, gender can take up to, it can take two values, right? It's either female or male. So basically here, what it's telling us that the estimate parameter value associated to the male label is this one. Then you may be wondering what happened to female. So female in some sense is being absorbed here under the intercept. So when you want to do a comparison in terms of, you want to compare female against males, So then the intercept or the female is being used as the base label. Okay, so that's basically what happened here. So the rule of thumb here is that if you have two labels, right, you're gonna have one estimated parameter. You have three labels, there will be two estimated parameters, and then the other label will be used as the base label. Okay. All right, now let's do a little bit of predictive modeling. So let's split the data into train and test. Let's build a model on the train, and then let's use that to predict on the test. Okay. All right, so what we can do here first, let's split the data. So the scalar for that, let's use train test split. So splitting the data into train and test. So here, what we're doing is we are defining two data frames. One is going to be called train, the other one is going to be test, and we're splitting the data frame called DF. We're using 20% of our data to go into the test. Random state equals to 42. That's just for reproducibility purposes. Okay, so if I run these now, if I do train it, so yeah, so we have 80% of the data is now here. Okay, so we were able, yeah, so we have our train or test. Then we can build the model. So building the model on the training data set. So I'm gonna call it LMMD equals to OLS. We're gonna use the same model, or yeah, the same configuration for the model that we have here. So let's copy that. Let's paste it here, but we need to update something. So here it needs to be train. We're building the model on the train now. Okay, and let's print in the summary. Okay, so yeah, so then here we have the estimated parameter table. So now with this model that we built here on the train data set, now we're gonna use that to make a prediction on the test. So predicting on the test. Okay, and then we can take a look at those predictions. So here are the predictions. Okay, now if you want to quickly compare these against the actual values, so you can easily create something like this. So pd concat predictions. Yeah, we can do something like this. Yeah, so this is the actual calories value. This is what the model is predicting. So it's 173, and the model predicted 170. Here indeed for this observation it was 189, and the model predicted 192, and so on. Okay, so you can visually see those two things. Oh yeah, a more concrete way to quantify model performance is by either computing the mean square error or the root mean square error, which we can easily do that here. So from sklearn matrix, import, let's use the root mean square error. So calculating the RMC, so root mean square. So yeah, so calories, so that this will be the true values from the test data set. This is what the model is predicting, and then let's print that. Okay, is 11.48. Okay, so how do you or what is the rule of thumb here when it comes to the root mean square error? Is the smaller that value is, the better the predictions are. Okay, but just by looking at that number by itself, it doesn't provide much insights other than uh, other than seeing how close that is to zero, but it will be more useful when you have 2 or 3 models and then that you use for prediction purposes and compare the corresponding root mean square errors. So then at that point you can easily tell, okay, this model is better than the other ones. Okay. So, but that's basically what I wanted to show you in this tutorial, is just how you can use the stats model formula library, or the stats models library in general to build linear regression models. Okay, so that's all I have in this tutorial. See you on the next one.